A 5-gram sample of an organic compound X contains carbon, hydrogen, and sulfur. It was analyzed in a combustion analysis, and you come up with 11.97 grams of carbon dioxide. 2.45 grams of H2O were collected. What is the percent carbon in the compound X? All right, now percent carbon. Now for combustion, we know that I'll just put CXHYSZ as some random organic compound plus oxygen yields H2O plus CO2. The reason why I'm writing this is to show you that combustion is a set equation. It's not going to change. It's always you're adding oxygen and you're creating H2O and CO2. So from this, we can say that the only source of carbon in the products is the CO2. So if we find the amount of carbon in CO2, that is the same amount of carbon from our original organic sample. The same thing goes with hydrogen and water. So the amount of water given can directly tell us the amount of hydrogen in the organic sample. This is not true with oxygen because there are two sources of oxygen from the left side of the equation, right? Or, well, usually there are. If this was instead of sulfur, this was oxygen, it'd be two sources. But the oxygen is usually provided in excess. So we can't determine anything from the oxygen yet. Or in this case, even the sulfur yet. So anyway, with this being said, we know that we have 11.97 grams of CO2. We can divide this by 44, which is the molar mass of CO2, to come up with 0.272 moles. This is the moles of CO2, which also equals the moles of carbon. So because it's a 1-to-1 ratio of carbon to CO2. So now from this moles, we can multiply it by 12. Times 12, we get 3.26 grams of carbon. This is the amount of carbon in the original sample. The original sample is 5 grams. And I know it's a 1-to-1 ratio because CO2 and carbon is 1 carbon to 1 molecule, right? So it would be the ratio between oxygen and the molecule would be 2-to-1. From carbon to the entire molecule would be 1-to-1. So we would take 3.26 divided by the 5 at the original sample, and that gives us 65. I got 65.3, but I think I rounded differently, but it would be 65.4. So that'd be the percent of carbon in the sample. All right, next, we do the exact same thing with hydrogen. So hydrogen, the amount of water is 2.45. So 2.45 grams of H2O, dividing that by the molar mass of 18. Okay, so that question of, the part of the question where it says grams of hydrogen and 100 grams of X, basically it's just saying that's another way to think about percentage, is really how many in a 100-gram sample, how much hydrogen or how much carbon you're going to have. But I don't even look at that. We know about mass percent, so that's kind of what it's asking. So 2.45 divided by 18, we get 0.136. This is moles of H2O. So now we're looking for moles of hydrogen. So if we multiply this by 2, we get the moles of hydrogen. Because just unlike carbon and CO2, which had a 1-to-1 ratio, the ratio between hydrogen and water is 2-to-1. Because in every 1 water molecule, there are 2 hydrogens, right? H2O. So we can say that there are double the amount of moles of hydrogen in some amount of water. So now from this, we can multiply it by the molar mass of hydrogen, which is about 1. So we can say we have 0.272 grams. Take this 0.272 grams, divide it by the total grams of the sample, which is 5, and we get 5.4%. So that would be B. All right, the last part, bring it home. What is the empirical formula of the compound? Now that we have the mass percent of carbon, the mass percent of hydrogen, we can simply find the mass percent of sulfur by taking 100 minus those two values. So 100 minus 65.4 minus 5.45, and we get 29. So I'll put sulfur up here, 29.15 grams. And I know it's percent, but I'm putting grams for now because remember, when we first learned how to determine the empirical formula, we've converted the percentages to grams, and then we determined the moles, and then we divided by the least amount of moles to come up with the ratio, right? So the sulfur is 29.15, the hydrogen is 5.45, and the carbon is 65.4. These are all grams. We can convert them to moles. So 29.15 divided by 32.06, that is 0.909 moles. The grams to moles for 5.45 grams of hydrogen is about 5.54 moles. For carbon, 65.4 divided by 12 is, again, so that's 5.45 again. So now we have the moles of each one. I'll put up here moles. We're going to divide by the least amount of moles, which is 0.9. 0.909. That equals 1 sulfur. 5.45 divided by 0.909. That is 5.99, which is very close to 6. So it'd be 6 hydrogens and 6 carbons because that's the same number of moles. They're a 1-to-1. Okay, so the answer would be, what is the empirical formula? It is C6H6S1. A certain carboxylic acid contains carbon, hydrogen, oxygen, and nitrogen. Combustion of 2.175 grams of the compound produces 3.94 grams of CO2. So you can write this information down. So 3.94 grams of CO2, 1.88 grams of H2O, and that's it. In a separate experiment, 1.873 grams of the compound was found to contain 0.359 grams of nitrogen. Okay, so we know that the ratio of the percent of nitrogen is 0.359 grams to 1.873 grams. That's the percent. So total, and then percent nitrogen. Okay, so using all this information, we should be able to figure out what the compound is. So, and also they give you a scheme of how to do it. So let's try to figure out the moles of carbon in the sample. So moles of carbon in the sample. We're going to take the grams of carbon dioxide. We're going to divide it by the molar mass. Divide by 44. And we're going to get 3.7. You get 0.89 moles of CO2, right? And that equates to 0.89 moles of carbon. Good. Next, we have the 1.88 grams of H2O. So we can just divide that by 18, just like we did before, and we'll get 1.88 divided by 18, 0.104 moles of H2O, which equal 0.208 moles of hydrogen. Okay, so let's look at, we already knocked out the first 4 problems from here. So you see moles of carbon in the sample compound, 0.89. Mass of carbon in the sample compound. Multiply 0.89 by 12.01. You get the mass in grams of carbon. Moles of hydrogen in the sample. Well, we look at the water component of the production by combustion, and we get 0.208. The mass is 0.208 times 1.008, which is the molar mass of water, and you get whatever that is. Now, the mass of nitrogen, the question. What's the 44? 44 is the molar mass of CO2. Sorry I did that part a little bit fast because I repeated it from the last problem. So now, mass of nitrogen in 2.175 grams of the sample. Because if you remember, the original sample was 2.175. But that second experiment they did gave us the percent nitrogen in the compound, which we can calculate right now by doing the 0.359 divided by 1.873. And we get 0.192, or 19.2% nitrogen. So the question's asking for, out of the 2.175 gram sample, how much nitrogen do we have? So we take 2.175 multiplied by our percent 0.192 of nitrogen, and we get 0.42 grams of nitrogen. I'll put in sample. Okay, I did a lot of math right now. Does everybody follow? And if not, please ask questions. I did go through that kind of fast. So I figured it's good that they give you the scheme of how to do it because you can get lost. But basically, I'm using the components of the combustion reaction to figure out the carbon component, then the hydrogen component, then the nitrogen component, and then we can figure out the oxygen component from all of that information. Okay, so now we have 3 out of the 4 components. We have the masses of them. So the way to figure out the mass of oxygen is just simply subtract the masses of the other 3 by the total sample, which is the 2.175. So it would be 2.175 minus the mass of carbon, which would be the moles of carbon, 0.089 times 12, which is 1.07, minus the moles of hydrogen. Moles of hydrogen is about, or sorry, the grams of hydrogen, which is about 0.2. And then the grams of nitrogen, 0.42. So you do that math, and you end up with 2.175 minus 1.07 minus 0.2 minus 0.42. You end up with 0.485 grams of oxygen. So now, what can you do? You have everything. So you can figure out the moles of oxygen because you know the moles of everything else. You can figure out the moles of everything. What we can do is, remember empirical formula. The goal is to figure out the moles of every component and then divide by the least number, right? So we have the moles of carbon, which is 0.089 carbon. We have the hydrogen, 0.208 hydrogen. We have the nitrogen, which is just finding the moles that's in 0.42. So 0.42 divided by 14, you get 0.03 nitrogen. Right? Yeah. Then you have the oxygen, 0.485 divided by 16 is 0.03 again of oxygen. So we're going to divide by the lowest number. So we divide by 0.03 moles. So that means our nitrogen number would be 1. Our oxygen number would be 1. Our hydrogen number would be 0.208 divided by 0.03, which is actually 6.93. 6.93. That's close enough to 7, by the way. And then you have your 0.089 for your carbon divided by the lowest number, 0.03, and that is 2.97. Awesome, 2.97. So then this is about 3, close enough to 3, close enough to 7. You have C3H7NO. And that is your empirical formula for this question.